I2C buses are, how to use them. It's as simple as that. It's a kind of, for people who never really had to play with them before. So I'm basically going to go through what SPI is, serial interface, how to use it from C briefly, how to use it from Python, and the same with I2C. They're kind of related. Differences, SPI is simpler in simpler technology. I2C is actually simpler to use with multiple devices. SPI 4 connections, read, write, chip select, and the clock. You can read and write at the same time, so it's duplex. You need a chip select per client device. I2C, 2 connections, clock, and a read-write line, so you tend to want to do things half duplex. But every device has an address, so you basically wire them all in parallel. So that was the next slide. So SPI, clock, typically active, chip select, typically low, clock. MOSI, master out, slave in. So if you look at a client chip, it will also say MOSI, but that will mean it's the input on the client, because it's the slave, not the master, and MISO, master in, slave out. Because it's pretty simple, you can actually implement it in software just using GPIOs. Wiring it up, it's as simple as that. Connect MOSI to MOSI and MISO to MISO, but you might see it as data in and data out. And the data is clocked in, most significant bit first. Now the fun is, nobody got together and decided when you read, when you write, and what polarity the clock is. So there are actually 4 different modes you can run SPI in. You can have positive positive clock, negative clock. You can read on the leading edge, or read and write on the leading edge, or read and write on the falling edge. Most things use mode 0, but check. Want multiple devices? You wire all the MISOs and MOSIs in parallel. You have to have a separate chip select for each of the slave devices. If you're lucky, then the SPI master already has that. If you're unlucky and it only has one, you can kind of fake it with something like an LS138, which is a decoder chip, and it's got enables for high and low enables. So if you connect the low enable to the chip select and then you use GPIOs to set the output, you can kind of use the GPIOs to select which slave you're going to talk to. I didn't do a diagram for that because it's a bit esoteric, but anybody wants to talk to me afterwards, they can do. As I said, you can do it in software, so that is completely software SPI. In fact, that's a cleanup of SPI code I wrote for 6502 on a BBC Micro, using the GPIO port. And I drove an Ethernet interface with it. So, doing it on a Pi. By default on Raspbian, the SPI driver is not enabled and not installed. If you don't want to try it one off, you can install it for the session. If you want to enable it permanently, just comment it out of the blacklist file. Once you've done that, you'll have to reboot. So once you've enabled that, there will now be an SPI device available to you that you can use. So in C, it's just open the device. Right, if you can see, it's got 2.0 there. The 2 means it's SPI device 2. The 0 means it's chip select 0 for that device. And the reason I've got 2 and 0 here is this code is actually off of a beagle bone, not a Raspberry Pi, but it's exactly the same. The only reason I use a Raspberry Pi is because everybody seems to have them. You can simply write bytes out and read them in using the standard C read and write, or you could do a full duplex using an ioctal and a data structure. That is, there's documentation in the kernel docs directory if you want to go that route. I've never needed to use it yet. Python. Install Python dev. Get the SPI device Python extension from GitHub and build it and install it. So once you've got that in there, you now have a Python SPI device. So you can just do import it as normal, open it. In this case, I'm inconsistent. I'm opening SPI device 0, not 2, and chip select 0. So once I've got that, I can read and write bytes as before, or use transfer. If you go to, if you basically Google this device, you'll find there's a lot more methods you can do, but that's the basics for reading and writing from the SPI bus. As a little aside, as I said, it's the most significant bit on the bus, which means you've got to do some bit swapping. That's a piece of code. When I publish my slides, that's a piece of code that does an efficient bit swap for a byte. It can be useful. So, what have we got which is SPI, which is useful? SD cards. That's why everything uses SD cards to boot. All these little embedded devices use SD cards because they're simple to read and write. If you use it in legacy old MMC mode, it is just an SPI device with a data in, data out, a clock and a chip select. There's an Arduino library that allows you to read them and read a FAT file system off of them. I actually got a knitted toy that I knitted, which has got an Arduino in it with an SD card, and a digital to analog converter, and a little amplifier and a loudspeaker, and basically it plays samples off the SD card through the speaker when you molest the toy. What is useful on a Pi, because it doesn't really have any, that's a nice little 8-channel analog to digital converter. Again, just clocks, chip select, data into master out, and data out to master in. And there's that's about £1.50 from Farnell's that. So if you need analog reading on your Pi, use one of those. 8 minutes. Okay. I2C, sort of next-gen SPI, cut down on the connections. So we've got 2 connections, the serial clock line and the data line, and the data has both read and write. So to select any peripheral, you have to have its address. You can do this by GPIOs again. The code is somewhat more sophisticated, so I haven't got a slide showing it because I don't bother, because most things have got an I2C master on them. So, there we are, we have a bunch of devices on an I2C bus. The protocol is that a device only ever pulls the bus low. So to keep it high, there are pull-up resistors. The Raspberry Pi has them built in, so you don't have to worry about them. If you're doing it on a BeagleBone, you've got to put them in yourself. They're 5.6K or something like that.
4.7 is pretty standard.
Okay. But whatever. To the line, and there is a collision detection in there, so you can see if two. And there's also a thing called clock stretching, which means a device can hold the line down if it needs to take longer than the clock you're driving the bus at. Addresses are 7-bit, with the 8-bit being the read and write bit. If you want to write, you just write. If you want to read, you typically have to tell it the address and then read back from the device. Most things have multiple registers, so what you're actually saying is, I want to read to device X, register Y, so you write that, and then you'll read back the value from that. You can also find that a lot of chips support multiple reads, so if you read 10 times and you started with, say, register 10, it'll actually read from register 10, 11, 12, 13, 14, 15, and so on, provided they're all 1 byte big. Again, on the Pi, temporarily enable them. Now, I2C on Raspbian, you need two modules, so we can just mod probe them if we need them, or again, we can take one out of the blacklist file and we can add the other one to the modules file to ensure that gets loaded at boot. Right, another nice thing you might want to install the Linux I2C tools, which you can, again, with a Raspbian Debian type one, just like apt-get install them. I haven't actually got anything connected to my I2C bus, which makes it really boring, but if I had, the addresses would appear in the relevant place within that address map. If anybody wants to see this actually happening tomorrow, I will, as an aside in my tutorial, I will have my Pi and a monitor, and I'll have breadboards and things hanging off of it, so I can knock something up quickly and give a quick demo. So, I2C in Linux. I could probably slow down now. I really realise how quickly I've been talking. Again, just a header. Open the device. Again, this piece of code is off of a BeagleBone, I think, because I'm using I2C device 3. And the bone is 1 and 3, and 2 is used internally. So yeah, you want to write to a value, just the register and the value, and once you've selected the address, you can write to it, or if you want to read, then you want to write the register and then you read the value back. For Python, this time, unlike the other one, you don't actually have to build it. The SM bus extension, I2C bus extension, is actually already available as a package. So we just need to apt-get install that. Import it, open it. Slightly unlike the SPI one, it's a slightly different style of using it. So the SPI one seems to have you have a device and then you open the device. Here, there's a factory method that returns the device when you request it. Read and write data. Again, there's a bunch of APIs, but the typical ones, you just want to read some data or write some data back. That's with the obvious APIs. So, what's a good I2C device that might be useful on a Pi? That, which is an 8-bit GPIO extender. There's a nice 16-bit one as well. But basically, you can support up to 8. If you see that there's 3 address pins which allow you to tweak the base address. You find this quite typical because If everything just has a fixed I2C address and you want to have more than one on your bus, then they'll conflict. You can just end up talking to both of them at the same time. So most I2C devices have a way of strapping pins to change its address. We've got a reset line, useful if it goes wrong, just connect it to a GPIO and put it low when it starts misbehaving. An interrupt line, I2C has no way of supporting interrupts, not as a way of the device contacting us in an interrupt type situation. So what you do is you just connect an interrupt again up to another GPIO and you just say, oh, this device had something, I'll go read its status register to find out what it's moaning about. So we set the address range, we connect up our clocks and our data line, but we can ignore reset for now and interrupt for now. And we've got 8 GPIOs. And because I was bored about 18 months ago, and I had a very small Christmas tree on my desk at work, I made it into getting able to tweetable Christmas lights. As you do. So you could tweet it with a number and it would change its pattern. But it's basically, if you can see, there are literally just 2 connections to the Pi, which is the clock and the light. And again, we've got power as well, but the power is actually external. So there's ground and the 2 signal lines. I've got 2 of the same chip, so one of them has got the address set as all zeros and the other one's set as 001. And that particular chip is quite good at driving. If you got them all on at the same time, it's a bit near some current limit, but if you're just kind of flickering them and moving them around and so on, you're okay, you get away with it. Pi permissions, right. By default, you'll have to be root to run anything that wants to access these devices. But nicely, you can create groups. There's a couple of groups that you can add yourself as a user. So if your username is Pi, you can add yourself to the SPI group, the I2C group, and then you can run your Python without having to do it as sudo. You can just run it as yourself. Again, if you ever change a group and you find it doesn't work, log out your shell and log back in again. It's because you haven't picked up your permissions. Now, if you want to test I2C devices in a nice and simple way, one of these, the Bus Pirate, it's a little USB, open source USB device that you can hook up, and it supports, it's got a serial console, so you just type commands in the console. It's got SPI, I2C, JTAG, the UART, and a couple of ADC in and controls of power. So if you've got a new device and you want to test it and play with it without having to do too much work, you can just basically stick it into the breadboard connectors to it and use that to drive it. And well, I'm on time. Any questions?
Which is the fastest one? Have you got a variation of clock speed on this?
Yeah. I2C probably has again, it's down to how you lay it. At the high end, it's how you lay out your PCB and what things are up to. But I2C, the newer protocol, so it's got the faster clock. But they're all configurable. So,
if you want to know about I2C in detail, you should look at the NXP spec because it belongs to NXP. It's on their website. But the fastest I2C clock is a megahertz. But SPI has no limit. Lots of SPI devices will crank at up to 75 megahertz. So much faster.
I thought I'd seen 4 meg I2C devices, but
I think they do go at that sort of speed. I mean, I think I2C has a reputation for being slow, but as you see, kind of easier to use, and you don't need extra chip select lines.
yes. And I can't remember what NXP are called anymore, because they then became Trident, and then they became something else.
NXP.com.
That was Philips or whatever.
Yeah.
It's the nice, caring face of Philips.
Well, one of their divisions got sold off then and got renamed. Yes.
If you wanted to sort of use sensors over wireless, which would be for somebody who's not a software person, which would be the more approachable?
So I missed the start of that F1.
If you wanted to do sort of, let's say, environmental sensing, so temperature or something, over a wireless interface, which would be...
Well, this sort of protocol tends to be between, kind of within a PCB, between the peripheral trips and the microcontroller. So if you're doing it over wireless, that tends to be a bit higher level. So what you'd have is the sensor chip will probably be I2C talking to a microcontroller that talks the wireless over whatever.
But you could easily speak to these two gentlemen here about wireless, and they would have a lot to say. Tim.
So how far apart is your Christmas tree from your controller? What range can you get down an I2C bus?
Not very far.
Inches, I think.
Yeah. It was the lead, I've got a ribbon cable on my Pi and it's about that long. So the actual breadboard was about that far away from the Pi. And I wasn't driving it that fast because I didn't have to.
If you want a big one, use one wire or something like that rather than I2C.
I thought the monitor ID on VGA was actually I2C.
It is. I mean, HDMI and DVI, I didn't know whether it is on VGA, but definitely HDMI and DVI, the communication to the monitor is I2C. Because in the HDMI protocol, there's an EEPROM in your display that's got the details about what the display can handle, so that when you plug it into your output device, your set-top box or whatever like that, or your PS3 or whatever, it doesn't kind of communicate really high level with anything. It's literally just reading out of that via I2C down the HDMI cable.
So I mean, my point was you can actually get a fair length, although everybody knows how reliable the monitor ID stuff is.
Yeah, exactly.
But it was designed as a within circuit board.
Yes.
So